Hello everyone, this is Van Liang from Dallas actually. So today I'll do the video lecture to make up I think the lecture on October 2nd. This video will last roughly 30 minutes or probably less depending on my depending on how fast I grow things. Okay, let's get started. So here is some quick wrap up of the logistics for this couple of weeks, for the week after last one and last week. And more importantly, I want to point out the plan for the video lecture and tomorrow. So we'll focus on crack tip plasticity. We have touched on this issue before, but not in detail. So today we're gonna kind of look more carefully about the plasticity zone, or or we call it plastic zone, right in front of crack tip, and we look at how people in the past or researchers in the past have examined this problem, and we try to appreciate their efforts on the topic. Okay, so before we wander into that, so we need to first look at this principle of superposition. I think some of you might have learned this before, know this concept before, which will be great help. So basically, the principle of superposition states that for a linearly elastic system, the individual components of stress, strain, and displacement are additive. For example, the two normal stresses in x direction caused by two different external load can be added to get the total stress. I think here two normal stress should be the normal stress actually. Anyway, I'll update the lecture later on, and so you get the idea. So we have the bar, right? We have a bar here. We have what you call it a beam here, which has the loading component, two parts. One is tensile loading indicated by P, and then there's a pure moment indicated by M. The tensile stress developed in this beam can be written as the superposition of the stress induced by the P and also the stress induced by M. We know that for P, it's uniform on all the cross sections, which is P over divided by A. But the bending moment here, they're gonna generate different tensile stress or compressive stress when you change the position on this cross section. So you can define a local coordinate system indicating the direction of Y. And as you can imagine, if indeed the bending moment is in this direction, the beam will bend in this manner, and the stress on top of the bar, which is here, will be in tension, and on the stress in the bottom half of the bar will be in compression, and the magnitude of stress can be indicated by that equation, which M is the moment, I is the second I think it's called a moment of the moment of the second moment of the area. Is that right? I think I might miss some exact wording there, but you can check that out. So EI will be the bending rigidity. So I sort of, I think the second moment of area. Second moment, yeah, I think that should be true, right? Anyway, this Y is a local coordinates indicating the position on this cross section, and in this case, it's a 1D, right? Because we, the cross section, we use one parameter to indicate its position. So the whole point here we want to make is actually here. So on similar lines, stress intensity factors can also be added. actually there's something wrong here. I mean, can also be edited. So the K total can be, for example, in this two cases, okay. So in this two cases, you can see there is I wouldn't call this two cases, but there are two. Oh yeah, you can call it two cases. But so if this is one case, right, you have a notch and you have P, you have a bending moment in this direction. And this case, you have P, you have a notch, you have P, you have a bending moment in that direction. So you can see that actually, if this bar is the same bar, actually, the same bar, which means actually the bar is under loading, this two loading at the same time, right? That would be actually the bar will be under 2p tensile, but this M and M, they cancel each other, so we will just be pure 2p tensile test stress, right? So this means that actually the K total, you can write it in a separate manner, which is Ki A in case A and Ki B in case B. I should put A and B here. Actually, I'll do that. I mean, I'll update the lecture. So you can see that actually the K total actually for this the crack driving force, or you see the stress intensity factor for this crack, right, can be written in terms of the superposition or the addition, right, or the summation of these two parts, and it's here, okay. And then you can see that actually, let me see, and then equals to K1A plus 0 equals 1. I think there's something wrong here, but so well, here it's not that clear, the A and B actually, but if A indicates the tensile loading, then this should be correct, because this bending moment here cancel each other. So in the end, you're gonna just have the y sigma A square root of pi A plus 0. Okay, so I have put a homework problem actually for this principle of superposition, because it can be really useful when you do real application or real analysis of problems. So the homework, this problem actually is about one of my early papers. Actually, it's my first paper in grad school. I think it's paper number 2 on the publication list. So I put it there. So I just ask you to summarize what how we use the principle of superposition to simplify a relevant problem in that paper. Okay. That's important, and we're gonna use this in this lecture. No, in this PowerPoint. Probably not the video lecture, but will be in tomorrow's lecture. Okay. Well, here is an example actually. This is a more detailed element. So this one, I think there's something wrong with the annotation here. So, but you get a rough idea. Here is a one specific example. So let's consider a plate having a semicircular crack subjected to an internal pressure. So this is I would say a thin plate actually. Think about this as like a gas tank or something. Then or like a like in our lab there's a nitrogen cylinder, right? So in the nitrogen cylinder, inside is I think the liquid nitrogen. So the because the pressure is very high, right? And this is the cylinder, and then the cylinder will be a thin shell, right? So you can see, so there's the internal pressure here. Oh, that might not be a good example, but we're gonna go back to that. I think it should be okay. We're gonna go back to that very quickly. So so if you can look up the stress intensity factor for this specific geometry actually, where the parameter is given here. Which you can find in a handbook, obviously. So, and here the phi and the g has been given as a as we touched on earlier, this phi and g, they describe the rule of geometry, a specific geometry, different cases. So you're gonna have different phi and different g. Now, for semicircular crack, we know that because it's semicircular, right? Semicircular, right? And then we have this diameter will be 2 times this one, which means 2c gonna equal to 2a, or a equal to c, right? So we plug that in here, you're gonna see phi equals to half of pi, and g phi actually equals to like a 1. Because here a equal to c, then this one always gonna be 1. So that in that case, we can calculate this this K1 total, right? Let's look at again. So this total will be, because it's the internal pressure, right? So I think you're interpreting this. Hold on a second. A plate having circular canal temperature, internal pressure. Yep, I think that can be the gas cylinder case. You just so when this is the case, when let's say your internal pressure is so high, so you can just ignore the atmospheric pressure, right? So we know in a gas cylinder it will be tens of 10 times of the atmospheric pressure, which is 1.01, I think it's 1.01 times 10 to the power of 5 Pascal. But the pressure inside of the gas cylinder can be much higher, such that you can ignore the atmospheric pressure. You just assume there is an internal pressure, right? So, which is good approximation actually. So in that case, we have this study, which we had never looked at it before, right? We always say there's a far field tensile stress. So using the principal linear superposition or principal superposition, actually, we can turn this problem into 2 equivalent problems that we feel good about. So here, this figure just states that actually A, which is the case at hand, will be equal to the superposition of these 2. And these 2 are something we are familiar with. The first one is you have a far field tensile stress applied on this plate with this crack here, and minus the case that actually you have the far field case, and also you have a negative, or you call it like a compressive, like a pressure exactly at same as P. So these 2, we can see that this one equal to this one, and we know the solution to this one, and we also know the solution to this one. Then we can get this one. The idea is the solution to this one, is easily, this is literally 1.12, right? For this case, we have looked at this one before, and then you have phi here equals to 2 pi. You just plug it in, and you have the pressure equal to P, which is sigma, right? You have pi A. And this one, actually, you have a far field, but you also have a near field or local stress, exactly canceling the effect of the far field. So which means this one is equal to 0. So you can, in the end, you get this this K for this structure, okay? Which actually you can, because this one equal to 0, actually, this one is equal to this one. This is something that you can get from the principle of superposition. Okay, I think that's good enough. We can move on to next slide, which we're gonna look at the problem at hand. We're gonna decide. Today's topic on this two lecture topic is crack tip plasticity. Okay, so here there's some comment. So our linear elastic fracture mechanics assumes a sharp crack tip. Right, we already touched on this before, and so a sharp crack tip is going to induce infinite stress at the crack tip. But in reality, or in real materials, the crack tip radius is finite, right? It's never like infinitesimally sharp. It's finite, and hence the crack tip stress is also finite. Okay, this is one aspect. Another aspect is, in addition, inelastic deformations due to plasticity in metals or creasing in polymers leads to further relaxation of stresses. So here I have a comment. You can refer to reading assignment or homework 3 for more details on this. Actually, the reading assignment, which is problem 1 or homework 3, is about one paper actually by another guy. It's like a competitor to John Hutchinson, in the old days. He's equivalently good actually. He's not as good as I would say a writer as John Hutchinson, but he's technically equivalently deep as I see, as far as I know. Okay, so I would need you guys to read that paper carefully, which contains no equations. Actually, it's just qualitative description. Okay, I need you guys to really understand what is going on in that paper. It's like a review actually, and that's the reason. That's the justification for this homework. Okay, now we have comments that actually for metals with yielding, the linear elastic fractional mechanics solution are not accurate, right? Because we know metals, depending on its ductility, right? But there always will be yielding issue, right? Unlike glass, a brittle material like a glass, there's pretty much no yielding. It just breaks at some point. So the metals, by definition, there's some ductility, and that which means there's always yielding, and there's plastic deformation happening in the deformation when the metal is loaded, right? So a small region on a crack tip yields, leading to a small plastic zone around it. So for moderately yielding metals, the linear elastic fractional mechanics solutions can be used with simple correction, which means you modify. You can still, because it's monetarily like yielding, right? So you can let's say introduce another term, but still keep the framework of the theory, I would say, and that will give you adequately good enough solutions, or adequately good enough estimates to what really happens in a deformation. But for extensively yielding metals, which is most of the case actually, alternative fracture parameters like a crack tip opening displacement or J integral are needed to be used in order to take to account material non-linearity, okay, which we'll touch on later. For CTOD and J integral, okay. All right, small scale plasticity. So this is as I said, we're gonna look at people in the past, the researcher in the past, how they look at this problem, okay. So one thing you can do is we know the normal stress actually. We know the normal stress based on the elastic analysis. And when we look at the normal stress actually, which right in front of the crack tip, for the mode 1 field is of this form, which we didn't spend any time in class. Recall that actually we look at the mode 3, like the outer plane shearing case. But I ask you to on the textbook there is also a long length actually, quite decent amount of information regarding how they derive the mode 1 case. You don't have to remember how they do it, but I just tell you this is the result. You can similarly to the case of the mode 3, they can be obtained in this form, in this manner. And in the crack plane theta equals 0, you can plug in the 0 here, then easily you can sigma 1 equals Q1 divided by 2 pi r, okay? That's the normal stress right in front of the crack tip on the line that, or you see on the plane that actually theta equals 0. So after, as a first approximation, yielding occurs when this one actually equals to the yield strength of the material, right? That's just the first order. So we can, this way we can estimate we can get the first order estimate of the plastic zone size. Okay, this is a approximately this is an approximate estimate because of the fact that actually sigma yy is here is based on elasticness. Right? Remember, this sigma yy, right? This one actually is based on linear elastic fracture mechanics. Assumes pretty much no plastic zone. And we get that expression, and we say, okay, that one, and we're forcing that one equal to the unit stress. But in nature, when we get this, we assume no plasticity, right? So there is some you can see there's some conflicts here or contradiction here. But still, we take this as a first order estimate, and we kind of know that actually it's not that accurate. So this actually leads to this equation, the yield stress, which is the material constant or material property, right? Which you can get from the stress strain curve easily for whatever material, and then just force it equal to this sigma y, and this way you can get the Ry equals to this formula, which might look familiar to you. Recall that actually in homework 1, actually we used some calculation on this already. This is the formula actually. I believe this is the formula. Referring back to homework, I think problem 3 in homework 1, which is about estimating the plastic zone size of an aluminum plate. And I remember you guys did the estimation, and it's like 1/3 of the crack length, and we deem that actually the plastic zone is too large to be ignored, right? So if you forgot, I would recommend you to go back and refresh your memory on that. Okay, so we get this estimate, but we know this is not accurate, right? This is the first thing. I mean, but then Irwin actually have a little bit more detailed version of his theory. Okay, so he goes by like this. So when yielding occurs, stress is redistributed, right? Stress is redistributed in order to satisfy equilibrium conditions. The cross-hatched regions, I guess this one, cross-hatched hatched regions represents or should we represent forces active in the elastic analysis that cannot be carried in the elastoplastic analysis. Because of the reason that the stresses cannot exceed sigma y, right? Sigma unit strength, to redistribute this excessive force, the plastic zone size must increase. Plastic zone must increase, and this is possible if the material immediately ahead of plastic zone carries more stresses, right? So Irwin then proposed that actually plasticity makes the crack behave as if it were larger than the actual physical size. So let the effective crack size be sigma A effective, such that A effective equals to A plus delta, where delta is the correction. You can write down this equation that actually this term we can force it. We still use the framework on that the linear elastic fracture mechanics, but we instead of use A, right, we use A effective. I think that's the case, right? So equals to K equals to pi effective, and then equals to sigma A plus delta 2 delta sigma that one. Okay, all sigma delta will be equals to exactly equals Ry actually. Yeah, I need to check into that equations more carefully and get back to you tomorrow. But this is how he does it, and so to permit the redistribution of stresses, the area of A and B must be the same. So that's the how they determine actually in the end delta equals to delta sigma, delta star, okay, asterisk. And then if we follow that, the RP actually is 2 times the R, the RY we obtained early on, okay. So they call this the crated plastic zone size. And you can see from here, yeah, I mean, you can further define this Ki divided sigma yield strength to the power of 2, or the square of that. Is define that one as the plastic constraint factor, okay. And effective crack size equals to AF effective. Let me get rid of this. It will be equals to A plus 2 RY and equal to that one. So the effective stress in effective factor will be Q1 equal to that one, okay. And here there's an example. I think given the time, I'll stop here. Actually, it's already like 26 minutes. You're encouraged to go through these 2 pages to look at this example. Now you can see it's pretty simple actually. Just give you the V, the thickness, and the loading, right? And they give you the KIC and the yield strength, right? This is yeah, this is material property actually. And then they ask for the factor of safety, the safety factor against the crack growth for crack, give you the crack length. So the geometry is here, and you can get the K, right, by once again checking the handbook, but find out this geometrical parameter, and then you can plug in the numbers and get the corresponding things. I'll stop here. I hope this I would say definitely go through this this lecture such that we can move on to the next approach in estimating the plastic zone, okay, plastic zone size. So well, let's stop that, and you guys have a good evening. I'll see you guys in class tomorrow at 1:30 p.m. In PE 102. Okay, all right. I'll stop here. Bye bye. Thanks.